In this example, we'll look at how FloEFD, a CAD-embedded CFD tool for Solid Edge, can be used to analyze a flow and thermal management problem of an audio amplifier. Let's take a look at our Solid Edge model. You'll notice that because of the FloEFD add-in, there are a few additions to the interface, like the Flow Analysis tab for the command ribbon and the FloEFD tab for the edge bar. What you will see as we set up the CFD problem and ultimately look at the results is that FloEFD ends up feeling like an extension of your already familiar Solid Edge environment, and one of the keys to that is being able to work directly with your native Solid Edge model. A common way to create a FloEFD project is to use the wizard, which serves as a convenient roadmap to guide you through the setup of the basic definition of your analysis. Once you've completed the wizard, a new CFD project is created in your Solid Edge model. From here, you can complete the problem definition for the analysis you would like to run. This would include assigning items like material properties, boundary conditions, fans, and heat sources. These inputs are applied directly to the Solid Edge model by selecting the appropriate faces or parts. This approach is particularly convenient when you need to make adjustments to your CAD model because the analysis inputs are always in sync with your CAD geometry. Analysis goals are also assigned to the CAD model to extract extra key data of interest from the results. And as a last step of the setup, the mesh inputs can be given. One of the core strengths of FloEFD, which overcomes a long-standing bottleneck in the CFD process, is its meshing approach, with the FloEFD mesher handling a wide range of complex CAD geometries easily. At this point, we are ready to run the analysis to obtain the results. Once the run is completed, we can look at the flow and thermal results on our Solid Edge model. Here, we start by looking at the velocity field on a cut plot, with vectors showing the direction of the flow and the colors showing the speed of the air, and we can change the plot to have the colors display temperature instead. Surface plots give us a way to look at the temperature more three-dimensionally. We can rotate the model to see the temperature distribution, as well as use our probe tool to conveniently extract the temperature at locations of interest. Let's also look at the temperatures on the components inside the enclosure. Another powerful viewing option is to look at flow trajectories. These can be animated to give an overall picture of how the air flows through this device. And notice that with all these viewing options, you can see the CFD solution directly in the context of your Solid Edge model. So in looking at the results from our first case, we want to make some design changes to improve the cooling effectiveness. And this is where the advantages of working directly with the Solid Edge model drastically reduce the amount of time and effort required to explore the design space with CFD. One of the ideas that we would like to test based on our first solution is to shift the fan slightly towards the center of the amp. We are hoping to divert a portion of the incoming airflow more towards the central region of the board to cool those components better, while still maintaining strong flow through the heatsink. Additionally, we will go ahead and increase the length of the heatsink fins to further help cool the transistors. So we have set up a second family of assemblies member in Solid Edge that reflects these design changes. Now, all we need to do is to clone the setup from our Case 1 project to the new design, which we'll call Case 2. This new case now has the same setup as Case 1, so we are ready to run our next test. After running the second case, we can look at the solution to see the effects of the new design. Our cut plot shows that there appears to be more flow diverted to the center of the board, and that region appears to be cooler. We can see the same effect when viewing the surface plot. The Compare tool gives us a convenient way to compare the results from the two cases side by side. We can use it to compare a variety of results types, like the active scene showing the temperature distribution, or a table of our goals to quantify the temperature of our key components. This example shows how FloEFD for Solid Edge can be used to improve cooling effectiveness of the design of an audio amp. FloEFD puts the power of CFD directly in the hands of Solid Edge users with an easy-to-use, fast, and accurate analysis tool.